So now I'm going to do an example of regression analysis, and normally I do a lot of time series analysis and international finance, but I'm going to do something that's more in the field of urban economics. What I'm going to do as an example for regression is what's called Zipf's law. It's the rank size rule for city size. Basically, the idea is that New York City's population, the largest in the U.S., should be twice, which is Los Angeles, it's the second largest, or 3 times Chicago, which is the third largest city. And the idea is that rank times size equals K. So Chicago's a little below 3 million. Third rank, would be about 9 million, and so New York's population would then be 9 million. Doesn't really hold as much in practice. There is economic theory behind it, having to do with how cities develop and evolve, but sometimes to me it kind of seems like it's a little bit of almost like a coincidence, but we can test it empirically. So if rank times size equals K, then we can say, well, break these up, take the log of both sides. You can subtract the log of the rank. Natural log of rank is A, the constant, minus, this is actually log K. So log rank is constant minus beta times the log of the size, right? So it's just broken up using logs, right? So can we see if it holds in practice? Now, one thing to think about is how many cities do we include, and I'll talk a little bit about that. But right now, we're just going to test it for all the cities we can find. So I went to factfinder.census.gov, which is a lot of census data. It's the census website. I'm going to use U.S. Census American Community Survey 5-year estimates from 2017, and I took them from the census. I got the file, but I am simply going to post them on my website. I've got them up, and I'm going to pull from there. I'm going to pull those 30,000 cities. Right now, think about it. If you think about the largest city, New York, the largest cities might have over 1 million, but a lot of these cities are quite small, and we ought to actually make sure we get rid of zero size cities too. So we'll clean the data as we go. So we've got 29,323 observations. You look at the head. I've got this is the geo ID, which comes with the data. This is the name of the city. It's alphabetical. All the cities in Alabama starting with A. And again, some of these are really small. All right. And the dimension again is already up here. You can see it over here, but if you just run it, you can see it's 3 columns. All right, this is all places, which is designated by the census, and then I'm just going to make sure that I'm going to take data, and all the ones where column 3 is greater than 0. I'm going to just choose those, and I'm going to just replace my original data set, and you can see it drops a couple hundred of those. All right, it's about 300 get dropped, 250. Right? And so then the other thing is I'm going to make sure that I remove those NAs, right? You might actually be blank, although I don't know exactly if any are going to get removed. No, there are no NAs. And so remember, if data are not available, you can actually do different things with them, although sometimes your code won't run. And so na.omit is to leave those out, but there's exclude and there's some other functions too. But that actually wasn't a problem. All right. One thing to look at is what is the average city size is about 8,000 people. So New York has 10 million or so. So that's actually pretty small. So I'm going to say, well, let's keep the ones that are population greater than 1,000, just in case, because again, we got Akron Town, Alabama is 318. This will actually drop it in half, basically, right? So we're going to just keep the population above 1,000. And that's actually something I'm going to talk about is where do you choose that arbitrary point, right? Where do you cut it off? Right, so now I'm going to make a data set and call it data 2. It's going to be logs, natural logs, and it's going to have new values in it. All right, and then notice the negative sign on rank. I'm kind of explain that here. So I'm going to call it data 2, and I'm going to make combine the columns of rank, right, of these two things separately. All right, so log of data 3, all right, is just simply the natural log, right? So that's the size part. And then the rank part is the order in the column. But you have to note that, is New York going to be ranked number 1, or is it going to be number 15,000? Right? So putting the negative on there actually is going to rank them backwards, because you're essentially sorting negative numbers. And so New York is going to be the largest negative number. It's going to be ranked 1. All right? And so again, I'm going to make 2 columns. One is log of the rank, and that's how you get the ordering of the 15,000. Right, with New York is number 1. And then this is simply the size, or New York is 10 million or whatever, and this is the log of 10 million. Right, so those two things go in there, and if you look here, we're going to have 2 columns. Right, and notice this is column 1, all right, and then which is a very, very large number, and then but these look fairly similar, right? Because it's going to have, and these are natural logs, right? Now I'm gonna give them names, right? And actually, if I rerun the head here, you can see that I've got ln rank and ln size, right? So these are natural logs. They look very similar, but again, this is has to do with the fact that it's thousands and millions, right? Now, first of all, check out if it's a data frame or not. It is not a data frame, so I will make it a data frame. All right, so now I've got a data frame called data2, right? And it's the same observations, just doesn't have the geo ID and it's transformed. Right. Now, I'm going to look for New York. There's a couple ways to do it. What is the maximum value for data 3? Right, and so this is 8,560,000. Right, I said New York was 10 million. I was a little bit off, but again, Chicago is 3 million, a little under, and to triple that, you know, there might be something accurate, but we're gonna actually test that. All right, so this is what I'm going to do here. I'm going to go to my data, my original file, which has those names, and has the names of the places in it, and I'm going to find the one where this maximum data 3, where data 3 in data is equal to the maximum value that I just called here. So I'm saying, where is data equal to this number? And so I'm going to pull only that row. So again, it's going to pull that row, and then it's going to give me all the columns for it. So if I run this, it's going to return this one row from data where the population is equal to the maximum. Right? So New York City, New York, here's the population here. Right? Now, if I find it in data 2, which has the ranks, the log rank and the log size, I can pull it here. And again, this is the ln size is 15.9 million. Well, remember, that's a log. How do you undo a log? You take the exponent of it. So I'm going to take the exponent of this. All right, so read this code here. I'm going to get this number, essentially. I'm going to take the exponent of 15.96. And say where in data 2 is, and so this is going to return a row from data 3 where we'll get the maximum population, all right, and we're going to say where in data 2 is that row, and return just the first column of that, right? So we see here that this is New York's row, and the rank is 1. And what this basically I'm doing here is checking to make sure that it's ranked 1. So the largest size is given the rank 1, right? And again, here we can do the exponent of a log, right? And so what I did here was call column 2, right? And so if I run this gave me this was column 1, which was the rank. This is column 2, which is population, right? So basically took the exponent of that log. This is the log. Undoing the log gives you the original number. So the exponent of a log gives you your original number, and you have the population of New York. All right. So the rank is 1, population is here. This is just a check of data, but it also kind of shows us how we can manipulate it. All right. So now we're going to do what we are setting out to do, which is the regression analysis. We are regressing log rank on log size, which is the formulation I showed above. I don't have to give it any more information because I say the data is data 2, which is the new data I made, which has those variables. So these are the names I gave them, this is the other name, and this is the data set. And if I run this, I make an object that is that regression. All right. Now, pulling the summary gives me traditional regression output. We've seen that before with some manufactured data. Right. So here's the intercept. All right. Here, and again, it should be, and in theory, this should be the log of the New York population. Right. And what did we say it was? It was 15.96. So it might actually be pretty close. All right, we can pull it. Actually, I'll pull it up here. 15.96. Right, so this is actually pretty close to what you would expect. Right, the intercept is the log population of New York, and then if we look down here, this should be -1. It's not. All right, so the coefficient. Remember, the beta should be 1 because in our original transformation there was no number attached. So here we're saying that this is actually a little bit lower than would be expected. Okay, so. We look at the rest of it. You see the t-values are extremely huge. The probability is basically 0. Standard errors, again, is pretty small. So, and R squared is ridiculously high. So this is a pretty solid bivariate regression. But this is actually lower than what would be predicted. All right. So. That's it. So that's kind of the question we'll talk about. Is the intercept significantly different? Is the slope? How would you measure that? Now I said it is, but how would you actually test that? We'll talk about that in lab. What specifically we do that, and then also in lab we'll interpret what that means. Okay, so essentially, if this is underperforming, that's saying that the rank size rule holds. Now if you go up here, and basically saying that this is too small, right? So if you were to plug in 3 million, that would predict actually a smaller city than New York. So is New York too big? Is New York too small? Or maybe Chicago's too big or too small? So that's something to think about. All right, and then, but we did this for the 15,000 cities. What about 100 largest cities, right? And one way to do it is you can make data 3, which is data 2, right? But you can say, well, which of them has a rank of less than or equal to 100, right? So this is going to subset, right? That's my way of subsetting. All right, so which of these, which rows have data ln size less than or equal to 100, and we're going to see that the dimension, now there's going to be ties here, right? So 99, because again, what happens if two cities have identical size? Then they might be tied in there. So, but anyway, 99 come back. I could find and fix it, but I'm going to just do that with 99. And then the head, right? You can see here that it looks pretty much what we've seen before. You can see that these logs are all really close. Reg 2, which is my second regression, is OLS as before, and then the summary here. Okay, and then if you look, this intercept actually gets a little smaller. This becomes less correct, right? And ln size actually gets even more incorrect, right? So maybe there's something that has to do with sample size, what we choose, right? So just something to think about. This is not the New York population. It should be closer to 16. This is not -1. All right, so maybe this doesn't hold. All right, and we'll talk in lab about a different population cutoff as the assignment. All right, one more thing to think about is if you run this. Right, you can actually split this up and get specific numbers. This gives you the call, which is not super interesting for what we can do later. But look at summary reg 2. If you just take like the fourth element, you're kind of separating this out. This gives you just the line with the results, and you could break it up further. Maybe you can just choose the estimate and the probability, or the estimate and the t-value. So you can actually take this result and subset it even further. Right. So, what I'm doing here and what we did is we're testing a regression for an actual urban economics question, which is the relationship between the ranks and sizes of cities. Take the original Zipf's law constant, right? Rank size is a constant, break it up into logs. We're assuming that this should be the New York log population, and this should be 1 or -1. And we're going to see if it holds in practice. And we did that. We pulled data from the census, and we made a data set, removed any NAs, cut the population off at a certain threshold, and then we took log rank and log size and did the regression. And we showed that it actually is different answers for different sample sizes, but we can go further and see if this law holds in total.